Hello everyone and welcome to your 19th lecture in Historical Geology. This is Dr. Hurt. We are moving right along through Earth's history. We've already finished the Hadean, Archean, and Proterozoic eons. We're headed now, beginning the final eon, the Phanerozoic. And surprisingly, the rest of this class, it's just about the Phanerozoic, which is only a small amount of Earth's history. It's only 542 million years of that 4.55 billion years that have elapsed since the Earth accreted. So it's kind of funny, so much of our class is just focused on this last eon, the Phanerozoic, the Paleozoic being the first era of that eon. So a lot happened. We have a lot more information about this eon than we do. Well, we're living in it right now for one thing, but we have a lot more information about the Phanerozoic, so we can say a lot more. So we're going to explore some of the major, massive changes that occurred in this time. You can see this looks, very different than the pictures that we've been looking at so far, right? You can see that life is abundant, and not only life, but animals, very sophisticated. I mean, this looks much more like what we're used to than, life in the Archean or Hadean, or well, there was no life in the Hadean, but things that we've looked at so far, right? This looks much more like normal life, okay? So still things are a little different, right? But you can recognize these things. Obviously, you recognize there are things like sharks and fishes and things that look like rays and reptiles and amphibians and things like that. So all the kind of very familiar species came into, well, not familiar species, but familiar phyla came into existence around this time. So anyway, we're not going to talk so much about life today. We're going to focus mostly on the geology of the Paleozoic today. But then next lecture, we'll start talking about that kind of more interesting topic of life changes that occurred in the Paleozoic. So again, we have finished with the Proterozoic, Archean, Hadean eons. We are moving right along into the Phanerozoic eon. And the first era that we're going to talk about is the Paleozoic. And we're going to talk about geology today. Then we'll talk about life in the next lecture in the Paleozoic. And remember, you do have to know all these periods of the Paleozoic, so just get them in your head, memorize them any way that you can. Got Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. Remember that the Pennsylvanian and Mississippian are part of the Carboniferous, so we kind of lump those two together in a single period. But anyway, that's how it all works, and that's how it all breaks down. We're going to talk about each of these periods today and just kind of major events that happened during these periods, okay? So that's the game plan for today, and this is our map of geologic time that we've been looking at. So we're just going to talk about this thin little slice of the pie today, the Paleozoic. Very thin slice, but a lot happened in that little slice. So here again are the periods of the Paleozoic. By the way, you should know these little symbols. A lot of times things are symbolized with these little things. So you have this weird looking C with a little cross through it. We use that for the Cambrian. And the reason we use that kind of weird C with a cross through it is because for the Carboniferous we use a C. So the Ordovician, instead of having just an O, we have that O with, again, a cross through it. That's Ordovician. Silurian is S, Devonian's D. Mississippian is M. Now, we kind of have a problem here because we have the Pennsylvanian, which is a P, right next to the Permian, which is a P. So the Pennsylvanian uses this like double thick P like that. Okay, so anyway, you should be familiar with those signs because sometimes you'll notice in the slides and other places in the homeworks, it'll just use those symbols instead of actually spelling out the period. Okay, so you got to be kind of fluent with this stuff. Now, remember that the Phanerozoic, the Paleozoic, and the Cambrian all started at this one all-important time that you must know for the test. It will be tested on in many different ways. 541 or 500. We don't know this date to exact number. So 541, 542 million years ago. Okay, sometimes I say 542. 541 is fine too. Okay, if you say 540, that's fine too. I don't really care that much. But you gotta know that date. That is an extremely important date because that's the date of the Cambrian explosion and the time that all life as we know it came into existence. Now, there was definitely life, of course, before the Cambrian explosion, but very kind of mysterious, microscopic, small. There's the Ediacaran fauna. It was we don't really even know how the Ediacaran fauna relates to the fauna of today, the animals of today. So this is a time in which very familiar life animals came into existence. So we're going to talk about that in the next period, or sorry, the next lecture. So you must know these periods of the Paleozoic. You must memorize them. You must know them for the test, okay, because they will come up. So Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and the Permian, okay? You also must know the start and beginning dates of the Paleozoic, okay? So it starts 541 million years ago. It ends 250 million years ago. If you just know 540 to 250, that would be fine, okay? So again, here's our kind of patchwork quilt of what Laurentia looked like at the end, the close of the Proterozoic, right? So the stuff that's shown in the olive green color here, these are parts of Laurentia that were added during the Paleozoic. So all this other stuff, this was all during the Proterozoic and Archean. Okay, so this is basically what the non-olive green stuff was all stuff that was around during the Archean and the Proterozoic. Okay, so it's all what we call Precambrian, so before the Cambrian, Precambrian origins. Okay. If you call them terrains, if you call them orogenies or origins, all those terms are fine, okay? So the major Paleozoic origins of North America are as follows. You have to know these. These are very important, okay? You should know, you don't have to memorize all of these. You can see there's a million different terrains and orogenies from the Proterozoic and Archean. You don't need to know them all. You do need to know the Grenville orogeny, and you do need to know the Yavapai, okay? Because those I could ask about. And you simply need to know, all you need to know about those, I want you to know, is that those were Proterozoic aged orogenies that occurred with the accretion of the supercontinent Rodinia. If you know that, that's great. That's all I want you to know, okay? So moving along, these are very important orogenies you should know. So first one, the Appalachian orogeny. And the Appalachian orogeny, you'll see, actually consists of a lot of different separate orogenies. So it's not just one. There's a lot of different mountain building events, aka orogenies, right, that happened during the Appalachian orogeny. So we'll talk about all those break that down to all the different orogenies that created the Appalachian Mountains as we know them today. You need to know the Caledonian up here off the coast of here in Greenland. You need to know especially the Cordilleran. The Cordilleran orogeny actually goes all the way from North America down through Central America and even into South America. Okay, it's a huge orogenic event. And again, just like the Appalachians, the Cordilleran area consists of a lot of different separate orogenies that we'll talk about. So, and then finally the Ouachita. And the Ouachita is even kind of connected to the Appalachians, but you need to know the Ouachita orogeny. This is an orogeny that created a lot of the mountains that you see throughout Texas and Oklahoma, Arkansas. It's all part of the Ouachita orogenies. Okay, so like things like the hill country there north of San Antonio, which is kind of probably the closest mountains we have to us here in Corpus Christi, at least on the U.S. side. Those were part of the Ouachita orogenies. Okay, so anyway, let's take a look at the Paleozoic, North America and the Paleozoic. So remember, we don't call this North America yet. We call it still Laurentia or Laurasia. A lot of things happened here. So first of all, we have the Canadian Shield. Okay, there's the Canadian Shield. Those are Archean. That's a stable Precambrian rocks exposed at the surface because it's a shield. Remember that shield are these cratonic rocks exposed at the surface. Okay, you can see that the beige area that you see here, all this beige color is platform. So again, these are kind of Precambrian rocks that are buried below superficial sedimentary rocks. Okay, some important things that we're going to hit on today. We're going to hit all these basins. So we're going to talk about the Williston Basin there in Montana, North Dakota, into Canada. We're going to talk about the Michigan Basin. We're going to talk about the Permian Basin. Some of these things, like the domes, we're not going to talk about these things. The Cincinnati Arch, we're not going to talk about. But we are going to talk about the Appalachian Basin. And we're going to talk about the Appalachian Mobile Belt, the Ouachita Mobile Belt, and the Cordilleran Mobile Belt. Okay, so those are the things we're going to kind of hit on today. The beige color, again, that's the Precambrian craton that's covered with sedimentary rocks. Remember that cratons covered with sedimentary rocks, we call that the platform. So this beige color is all the platform. Okay. So let's take a look at how Laurentia looked, aka North America looked, during the early Paleozoic. So this is Middle Ordovician. Remember, we go Cambrian, Ordovician. So this is pretty close to the beginning. Cambrian is, of course, the beginning period of the Paleozoic, but Ordovician's, not too far along either. So remember that we're kind of turned on our side here. So like this is, I hope you can kind of orient it, but this is would be like Mexico and our east coast right now. And you can see that we're kind of turned like 90 degrees on our side. I guess it would be clockwise rotation. So we're also pretty close to, or actually not pretty close, we are on the equator. So Canada was on the equator at this time. And you can see that we are surrounded by a few different big continental land masses, one of them being Baltica, Siberia, and Avalonia. Okay, so we'll talk about how those things relate to and how they interacted with Laurentia throughout this lecture. So sea levels in the Paleozoic were very high. You can see, this is kind of crazy to think about, but you can see that, okay, so this you see how there's kind of dark blue color here? That's deep ocean basin. So that's actual ocean crust, okay? Now, the shallow seas that you see, like right here, this lighter blue color, that area consists of continental crust that is flooded with seawater. So during this time, even though there was a lot of surface area of continent exposed, that continent was not as thick as it is now. So it had a stronger tendency to be flooded. And also there just at this time was not as much ice as there is now. So there was, again, a tendency to have higher water levels, and a lot of the continents were totally underwater. So you can see that North America was mostly underwater. If you can believe that, North America was mostly underwater. Right now in Earth history, we are at a point in which the water levels are at almost historic lows. Okay, so most of Earth history, you'll find water levels were significantly higher than they are right now. And a lot of the continents were flooded. They were totally covered by shallow seas. You can imagine, kind of just Corpus Christi almost gives you an idea of what this area would have been like. A lot of this area of Corpus is surrounded by these shallow seas, right? So there you can go out. I mean, you know what it's like. You go out into the bay and you can wade out into the water really far, right? Because they're very shallow. So you could imagine there are vast parts of the continent that were like this. So these shallow seas are called, another term for them you should be familiar with is epiric. So epiric seas, okay? They're just continental crust that is covered with water. So here's kind of a breakdown of what we had in the Precambrian. So remember that last time we ended with the Precambrian, we ended with the Proterozoic and this first supercontinent of Rodinia. So I hope that sounds familiar. Rodinia kind of came together during about 1.2 billion years ago, and it survived to about 0.75 billion years ago, which is 750 million years ago. So by 750 million years ago, which is, remember, still in the Proterozoic, we have the initial breakup of Rodinia. Okay, so we're going to look at how Rodinia broke up during the end of the Proterozoic into the Paleozoic. So here we go. You see that Laurentia here, which is North America, is surrounded by the Kalahari, which is kind of South Africa, the Congo, which is kind of mid-Africa, Amazonia, which is part of South America, and Baltica, which is part of Europe, part of like Western Europe. Okay, so and then to the north of Laurentia is part of China, South China. Okay, so let's see what happens. Going into the Paleozoic, beginning this breakup, you can see that Laurentia starts to separate off, and you get Kalahari breaking off and creating East Antarctica and Australia. So these new continental land masses come into being from the split up of the Kalahari, right? So you can see how that all goes. So Baltica is still attached here, Amazonia, but it's starting to break up. So ocean basins begin opening up 750 million years ago, ripping Rodinia apart. Okay, so here by the late Cambrian. So Cambrian, remember, that's the first period of the Paleozoic. We have Laurentia here, and now, so by the time we get into the late Cambrian, you can see Laurentia is basically by itself. Okay, it's been totally ripped apart. There's Baltica has ripped off, South America has ripped off, right? All of Africa, Siberia is all ripped off, and we're by ourselves. Remember, we used to have China connected to us, Baltica, South America, Amazonia, Siberia, all those things used to be connected to Laurentia. So by late Cambrian, we're basically by ourselves, free floating by ourselves. Okay. However, kind of like thinking of like those Wilson basins. Remember how the Wilson cycle, you would open up these oceans and the oceans would close again, right? So this is kind of the story of the Paleozoic. The Paleozoic, you start off at the end of the Proterozoic, you start off ripping Rodinia apart, and the whole story of the Paleozoic is Rodinia being ripped apart and then coming back together to form a new continent, a new supercontinent, which is Pangaea. Okay, so we're going to start off by ripping apart Rodinia and then putting it all back together, putting the pieces all back together to form Pangaea. Okay, that's just the second supercontinent we're going to study. So you can see that already by the late Cambrian, we're all alone here in Laurentia, but these subduction zones have opened up. Okay, so that means that China over here is going to start approaching Laurentia. And this ocean basin, which is now, we call this the Panthalassoc Ocean, and the Iapetus Ocean, those are the two major ocean basins, are going to start closing up again. So at the start of the Paleozoic, the Cambrian, Laurentia had broken off from the mainland landmass, and most of the continents were assembled in kind of I wouldn't call it a supercontinent, but a very large continent that we call Gondwana. So Gondwana consisted of Antarctica, South America, and Africa. Okay, and also South China as well. So you can see that there are right now six large land masses. So those six large land masses are as follows. Let me point them out to you. So the beginning of the Paleozoic, we have these six large land masses. There's Laurentia, that's us, right? We're North America. There's Siberia, Baltica. There's Kazakhstania. There's Gondwana, which consists of a lot of different areas, right? You can see that South America, Africa, Antarctica, India, all these things are kind of conglomerated into this kind of, I wouldn't call it a supercontinent, but a large continent. Okay, and by the way, you can see this is all connected here. Is what this big continent, and then also parts of China. Okay, so those are the six big land masses that we have. Okay, so Laurentia, Siberia, Baltica, Kazakhstania, Gondwana, and China. Okay, so there's another depiction of it in the late Cambrian. It's kind of a little bit more clear, less complicated depiction. There's Baltica, Siberia, Laurentia, Kazakhstania, Gondwana, and North China. Okay. Notice there are two main ocean basins. Like I said, you have the Panthalassoc and the Iapetus, right? So good exam questions. I could ask you, hey, in the early Paleozoic, can you name any of the ocean basins that were around? So you should be able to, you should be familiar with those. So notice that the Panthalassoc is to our north, and the Iapetus would be to our south. Okay. So moving from the late Cambrian into the Ordovician. Okay, so look at how the subduction zones are set up here. So you can see that North America is surrounded by subduction zones here. So we have a subduction zone right here. So we might expect that the Panthalastic is moving this way. You can see that this part of the ocean is being consumed on two sides, right? So the North China side and the Laurentian side. So we can imagine that this is going to very quickly come together, okay? You can see that Gondwana is this little tag of ocean right here is going to get swallowed up, and you're going to have collisions between Baltica, Siberia, and Gondwana, right? So hopefully you can start to see these things. So let's move now into the Ordovician, and we might expect to see some collisions between Siberia and Gondwana, Baltica and Gondwana, and maybe China getting closer to America or closer to North America, Laurentia. Let's see what develops. Also, there's these little islands. There might be some collisions here. Okay, so you can see that here's Laurentia. You can see that the Panthalastic now, we still have the Panthalastic, but you can see that the Iapetus is starting to close up. Okay, we have this new part, kind of microcontinent, if you could call it, that's been created by the subduction zones. Remember that continental crust, new continental crust, is created at subduction zones. So this part is called Avalonia, which is part of Western Europe. Okay, so Baltica is getting closer to us. Avalonia is going to be getting closer to us. Siberia is getting closer. And we have this opening of a new sea we call the Paleotethys. The Paleotethys. There's actually little, and eventually that's going to become the Tethys. So you'll see that developing as we move along. Okay. So at the Ordovician, we have the microcontinent of Avalonia, which consists of Western Europe. It's detached from Gondwana, and the Iapetus starts to close. So we see the Iapetus Sea closing as Avalonia approaches North America, and we're going to have a major collision between Avalonia and Laurentia. That's going to be partly responsible for the Appalachian orogenies. Okay. Now, here we go, moving from the Ordovician to the Silurian, which is the next period. We start to see, again, the closing of the Iapetus Ocean. And you can see now, here's Avalonia right here. So Avalonia, you can see, is colliding now with Laurentia, and we're going to get the start of the Appalachian orogenies. So this is 425 million years ago. We're going to start to see the Appalachians rising up. Okay, so this is part of the Appalachian orogenies. Baltica, you can see that Baltica is now colliding with Laurentia as well. It's creating these Caledonian orogenies. Okay, the Iapetus is closing up. We still have now the Panthalastic is closing up more, and we still have now the opening of the Paleotethys and the Rheic oceans. Okay. So during the Silurian, Baltica collided with Laurentia to form Laurasia. So we're going to change the name of Laurentia to Laurasia. And that creates, like I said, the Caledonian orogeny. Okay, so what we have right here, let me erase the ink on here. So what we have, the mountains that are being created here in the dark brown, those are the Caledonians. And today we find the Caledonians in northern Scotland, in parts of Greenland, still in parts of North America and Maine, going through Canada. So we find traces of the Caledonians all through there. So the Caledonian orogeny was the closure of the northern Iapetus Sea. Okay, so again, this beautiful topography you see here in northern Scotland, the Scottish Highlands. Sometimes you probably heard of things like Highlanders, right, being associated with Scotland. So this is all topography that was created from the Caledonian orogeny. Okay, that's what's left of the Caledonian Mountains. And again, the Caledonian Mountains, probably at one time they were as high as the Himalayas, but you can see what they look like now. They're, hills, hilly country, high country, but not Himalayan. It's nothing like the Himalayan mountains are now. Okay, so moving, we went through the Cambrian to the Ordovician, Silurian, now the Devonian. Now you can see that, again, the Iapetus is totally gone. Okay, the Iapetus is totally gone, and it's totally collided. You see Now you might notice, where the heck is Baltica? Baltica is gone. Baltica has collided with Laurasia. Where's Avalonia? Where's it's all collided. Avalonia's gone, Baltica's gone. It's all collided and accreted onto the Laurasian landmass. Okay? Kazakhstan is collided with us. Siberia is starting to collide with Laurasia. Okay? So we get this big mountain chain that all ultimately becomes the Appalachian Mountains here. Okay? Furthermore, you see Gondwana is starting to close up too. And this is going to close up the Rheic Ocean. So the Devonian begins with the collision of Avalonia with Laurasia. That creates what's called the Arcadian orogeny. So the Caledonian orogeny. So the whole story of the Appalachians, a massive, it would have been at one time the size of the Himalayas. The whole Appalachian mountain belt, which goes from, like Georgia in our country all the way up into Canada. It all starts with the Caledonians in the north, 425 million years ago in the Silurian, and it continues into the Devonian, 390 million years ago. You're closing up the Iapetus, and you are creating another mountain belt with the Arcadian mountains. So remember, you have the Appalachians are really, I said, a conglomerate of different mountain building events. So it starts with the Caledonian. Second one is the Arcadian. Okay, so in eastern North America, if you can actually go to the Acadian Mountains now, which again are part of the larger Appalachian mountain belt. They're around New York, kind of New England area. So the Acadian Mountains were uplifted at this time. You had the Rheic Ocean, and as these mountains were uplifted, wind, waves, rain, ocean, snow are eroding these mountains away, and they are filling up these basins. Remember, like back arc basins we talked about? It's filling up these back arc basins, what is later called the Appalachian Basin. So the Appalachian Basin is getting filled up with all this sediment. Okay, so we have all this sediment build up in, like I said, what's called the Appalachian Basin. So the uplifted Acadian Mountains, which were heavily eroded, produced sandy sediments that flowed into the Catskills Delta. So you could imagine there's all these rivers. I could maybe draw this and maybe erase everything on here and draw this in blue. There would have been rivers, coming out of the Acadian Mountains, just bringing out all of this sediment, right? So you got all this sediment, and it's flowing into this shallow sea. Okay, so there's a shallow sea here, an Epiric Sea. And that Epiric Sea is filled in partly in part because of this was like a back arc basin, right? So you get these rivers bringing in all this sediment and creates a delta complex. So, deltas are where rivers reach the sea. So that's called the Catskills Delta, named after the Catskills. You might be familiar with this area. New York, Pennsylvania area has the Catskill Mountains. So it's similar, similar region as the Catskill Mountains. Okay, so again, this is kind of a picture, a side view of what would be going on. So you have Avalonia now, Baltica. The collision between Laurentia and Baltica created the Caledonians. The collision between Avalonia and Laurasia created the Acadian Mountains. So you have the uplift of the Acadian Mountains, along with subduction and collision. You're getting this mountain uplift. You're getting a lot of volcanism. Wind and rain come, erodes this material, and it fills into the Appalachian Basin. Okay, so you get the Appalachian Basin filled with sandstones, black shales, and carbonate rocks like limestone. Okay, so that's the Catskills Delta, and over here the Appalachian Basin. So part of the rock formations that were created during this time are the old red sandstones. So this picture you see here is a outcrop of a formation called the Old Red Sandstone. And what's really cool is that you can find this exact same formation both in America, North America, and in Europe. So, at the time, this was, right, Avalonia is now, this is now part of Europe, right, Western Europe. Acadia, on the other hand, this area, is part of North America. So although this accreted together, later in time with the breakup of Pangaea, this splits off again, and it goes its separate ways. One way goes to Europe, the other side to America. But the sand, you could imagine that as these Acadian mountains eroded away, sand was being deposited over here, as well as sand being deposited over here, and we get the same old red sandstone created on either side. So what's cool is that we find this exact same formation both in Europe and in America. So here's again the old red sandstone. It was a very popular building material in the medieval times. It was this is Goodrich Castle in the UK, which was built completely out of old red sandstone. So it's it was very popular, very hard rock, very good for building fortifications during medieval times. So anyway, moving along through time, we go through the Cambrian, the Ordovician, the Devonian, the Silurian, now into the Carboniferous. You can see that now Pangaea has even begun to come along. So we're starting to call this now Pangaea. So Laurasia, this is the Laurasian landmass, it's collided with Baltica. It's collided with Avalonia. Now the Rheic Ocean has totally closed up. Sorry, this used to be the Rheic Ocean right here. It used to be the Rheic Sea. It's gone now, and we've collided with Gondwana, the big honkin' big landmass that was around during the Paleozoic. So now there's this collision between Gondwana and Laurasia, and it's going to really finish off the Appalachians by giving us, this creates the Ouachita orogeny, the Ouachita Mountains, and so this is 306 million years ago. So you can see that the Appalachians were really under construction for hundreds of millions of years, right? So like 425 million years now to 300 million years. They've been under construction, under this constant uplift from collisions with Baltica, Avalonia, Gondwana, the closing of the Iapetus, the closing of the Rheic Sea, and now this brings us to the Carboniferous. You can still see that we have the Panthalassic, we have the Paleotethys here, and you can see that now Siberia and Kazakhstania have lumped together with Laurasia. So this is all connected. Even though there's this light blue ocean, this is all connected now, okay? Because it's just a Pyrrhic Sea right here, but it's all, the continents have collided and connected. And we're coming together now to create Pangaea. Okay, so into the Carboniferous, the Rheic Ocean closes, connects Gondwana with Laurasia, producing Pangaea, and the one kind of massive ocean, the Panthalassic, along with the Paleotethys, which you notice that the Paleotethys is starting to become kind of a closed basin. You see, it doesn't have, I want to point this out. Hold on. Let me erase everything on here. You can see that there's only this one thin part of the ocean that is actually, the ocean basin is connected with the rest of the Panthalassic. The rest of it is surrounded by shallow sea and continent. Okay, so the Paleotethys is starting to become kind of a closed basin, you can almost picture it almost like the Gulf of Mexico. Okay, so it's that kind of an ocean basin. Notice how subduction zones surround much of Pangaea and Gondwana at this point. Okay, so you can see that subduction zones are all along here, surrounding the entire Pangaea. Okay, that's a big deal because you can imagine that those subduction zones are creating volcanism, right? So it's kind of a unique situation. We're going to have volcanoes all along here. It's going to create mountains just like we have the Andes Mountains of today, all along here. So you're going to have these mountain belts totally surrounding Pangaea. So this was kind of an interesting time. So you could imagine if you were to go to the margins of Pangaea at this time during the Carboniferous, you would just find this continuous mountain belt totally surrounding the continent. This is a modern day picture of the Andes Mountains, but you could imagine this is what it would have looked like at the time. So these are subduction zones are producing mountains analogous to the Andes of today. Well, that's going to create some interesting weather on Pangaea at that time. Being totally surrounded by mountains, you might be familiar with this thing called the rain shadow effect. So a lot of times when you have an ocean on one side of a mountain, on the other side you're going to get very dry weather. Okay, so like you'll get deserts on the other side, and this actually happens in, for example, South America. We have the Atacama Desert. In California, we have parts of the Mojave Desert. We have, of course, what's it called? The Dead. Forgetting the name of it. Death Valley. These are all what are called rain shadow deserts. So what happens is that moist, wet air. Let me get my blue pen out. So warm, moist air comes in from the ocean, and as it comes in, it gets uplifted over the mountains. And when it uplifts, it's colder as you move up. So that those cooler temperatures cause the water to condense and for rain to fall. So as the air comes along the other side, so that air descends down into the valley on the other side of the mountains, it's going to be dry because it lost all of its water. So all this air is very dry, and it also, as it moves down and gets compressed, it warms up. And so that's just a very basic kind of thermodynamics of how air works. When it gets elevated, it cools down. When it moves down and gets compressed, and it heats up. So you get this hot, dry air coming on the other side of the mountain. So we think that during this part of the Carboniferous, a lot of the interior of Pangaea was like a desert. Okay, so you can almost kind of picture it like this is India, and this is India today. This is modern day India, and this is our China and the Himalayan mountains. The moist air coming from the Indian Ocean over India hits the Himalayan mountains. It produces some very wet. You see how wet and green it is right here? It's extremely green. And then when you get to the other side of the Himalayan mountains, it's brown and dry. Okay, that's what's happening. That's a rain shadow effect. So we're thinking that the interior of the Pangaean continent during the Carboniferous must have been like this. Very hot, dry area. Okay, you do get these deserts that form, on the other side here. Like you get the, the name is escaping me right now. It's the desert that goes through Mongolia, but it's very hot, dry conditions. Okay, maybe not necessarily hot. Maybe sometimes it's cold and dry, but it's very dry, and you get very desert-like conditions. However, along the coastlines, right, just like so, maybe it's hot and dry in here, but along the coastlines, it was probably very wet, and we see that reflected in the kinds of rocks that we are finding during the Carboniferous along the coastlines. We get all the rain being dumped. You get almost like what would have been almost like rainforest. Now, we did have terrestrial trees at this time, so we're going to talk more about the evolution of plant life in the next lecture. But at this time, during the Carboniferous, we had trees, we had forests, we had swamps, and we think that along the coast surrounding Pangaea, we get these very vast swamplands. Okay, so we can find fossil rocks during the Carboniferous that are just loaded with plants, loaded with ferns and plants. So the coasts of the continents were very moist. They formed many coastal swamps, and these swamps were eventually buried during sea level rise, which created the vast coal deposits that we see to this day. So the way that coal is, the reason we call this, by the way, the Carboniferous, carbon, coal, right? We call this the Carboniferous because there was so much coal created during this time. So you can imagine there were all these coastal forests, coastal rainforests, coastal swamps, many giant plants, and over millions of years, the plants were buried under water and soil, dirt, rocks, sediment, and once enough piles up on top of that dead organic material, you compress it and transform it into coal, right? So we have these beautiful, big, massive coal seams running through our country, providing quite a lot of energy. It's not necessarily very clean burning energy, but it provides a lot of very rich energy source, and a lot of people, of course, a lot of countries use this as their primary energy source all around the world. So these are all coal deposits from the Carboniferous. Okay, so these are coal seams in Alaska. This is a map just globally showing places where there are coal occurrences from the Carboniferous, and you can see that they are virtually everywhere, all across the world. Petroleum will probably run out pretty soon. And I mean by pretty soon, I mean like 100 years kind of thing, maybe a little more, but there's not a lot of petroleum left probably, but coal, on the other hand, is extremely plentiful. So there's enough coal energy to last a very long time. So just something to think about in terms of energy deposits. One of the reasons that there's so much coal in the Carboniferous is that there were a lot of terrestrial plants. There were trees. However, there was not a lot of fungus. Fungus, actually, believe it or not, some of you might look at fungus, like look at mushrooms and be like, wow, these are like ancient organisms. And that's actually not true. There are 6 kingdoms of life, right? There is, I'm just going to go over it one more time for review. There's bacteria and archaea. Those are the prokaryotes, right? From those, you get the protozoans. Protozoans mean the beginning of animals, okay? Those are things like algae, single-celled eukaryotic cells, so these are eukaryotes. And from those you get plants, animals, and eventually there's another split that creates fungus. So fungus, sorry, no, you can't see that, but there's fungus. Fungus actually comes late in the game. Fungus is the last kingdom to really develop itself. So during the Carboniferous, we had a lot of trees, but we didn't have a lot of fungus and a lot of mushrooms and things like that. And anyone who has, now, we don't have so many woods here in Corpus Christi, but anyone who's walked around in like eastern hardwood forests, you see all the dead wood, and you see the mushrooms basically eating the dead wood. That's what they're doing. They're decomposing it, breaking it down, helping it to rot. So without that fungus breaking it all down, a lot of the wood gets preserved. It's because it's more susceptible to preservation instead of breakdown. So moving along from the Carboniferous into the Permian. So the Permian is now the last period of the Paleozoic. You get the completion of Pangaea. Okay, so here's Pangaea, right? And you get these, what we might have called the Central Pangaean Mountains, which basically represents the suture of Baltica, Avalonia, and Gondwana with Laurasia. Okay, we call it Laurasia now because Laurentia has combined with Kazakhstan and Siberia, which are parts of Asia, so we call it kind of Laurasia, and also northern China, so we call it Laurasia instead of Laurentia. And you have this now totally closed off. I want to point out how now the Paleotethys is totally closed off from the main ocean. There are parts, of course, where it can hit the main ocean through these shallow seas, but it has, my point is there's a restricted flow. So this Paleotethys cannot flow very well into the larger Panthalassic Ocean, okay? Now you see that there's an opening of a new ocean. This is a new one. This is the Paleotethys. Now we're going to open up the Tethys, okay, 255 million years ago. And believe it or not, there are still little traces of the Tethys left on Earth right now. It's actually in the Caspian Sea. It's a very interesting, Caspian is a very interesting body of water. It's not as salty as the ocean, but it's also not fresh. And it is also has the oldest ocean floor. And so the Caspian's weird because there's actually ocean floor beneath the Caspian, actual basalt ocean, deep ocean floor. And that ocean floor is the remnants of the Tethys. So there's still little teeny weeny bit of the Tethys left on Earth there in the Caspian Sea, around the Urals, around Eastern Europe or kind of the Middle East area. So anyway, that's late Permian, 255 million years ago. This is what everything looked like. The Pangea has basically formed. The Appalachian Mountains were formed during this time, but the Ouachita and Alleghenian, by the Ouachita and Alleghenian orogenies. Okay, so this is going to be a little video just showing you kind of a summary of what we just talked about. I'm going to show it to you now. This is right here, okay? So this is the Cambrian, okay? Let me see, he has some nice music I guess I can turn on. Whoops. So here's the Cambrian. This is Laurasia right here, okay? And this large landmass is Gondwana. This is, let me see, I think this one is Baltica right here. And this is Avalonia. So you can see that Avalonia is coming closer. Oh no, I'm sorry. This that just broke off, that's Avalonia right down here. Okay, so we're expecting to see the collision. This is Siberia and Kazakhstania up here. So we're expecting to see Baltica first to collide with Laurasia, and then followed by Avalonia. So Avalonia is right there. Okay, so now we get the closing of the Iapetus, closing of the Rheic, and we're getting the collision now of Baltica and Avalonia during the Caledonian and Akkadian orogenies. Here's Siberia up here still. Okay, so this is the Caledonian and Akkadian. Now you see the closing of the Rheic. This is the closing of the Rheic right down here. That's giving us the Appalachian, the Ouachita and Alleghenian orogenies. Okay, so now you have the completion of the, or near completion of the Appalachian Mountains. And you see the closing of the Paleotethys, closing of the Rheic, and you get the completion of Pangea, or near completion of Pangea now. So Gondwana has collided with Laurasia. Now this is the Paleotethys right here. This is the Panthalassoc Ocean over here. Here's the Paleotethys. Okay, so we're in the Carboniferous now. Now look at this. You see this new opening basin right here? You see the closing of the Paleotethys. You see the opening right here of this basin. That is the Tethys. So the closing, this is the Paleotethys closing up. This is now the Tethys opening up. Okay, now we're in the Permian. This is Pangea. Okay, and I'm going to stop it now because we're about to enter 250 million years, which, as you know, is the end of the Paleozoic. Okay, so at the end of the Paleozoic, this is what we get, right? We have Pangea, we have the Paleotethys about to close over here, and we have the Tethys opening up over here. And guess what? It's these supercontinents are so short-lived. You know, it's kind of funny because the whole story of Paleozoic is, Rodinia is broken up and it comes back together as Pangea, and now the whole story as we move into the Mesozoic is going to be the story of the breakup of Pangea. So these massive supercontinents do not last very long. It doesn't take very long for them to break apart. The reasons for that are interesting, but I'm not going to get into them. It's a little bit too deep for this class. So anyway, that's a pretty good video, and I hope that you'll be able to go through that video and recognize, without the labels, be able to recognize kind of the main continental land masses, the different collisions, the names for the different collisions, and be able to make sense of it all. Okay, so by the late Cambrian, there you go. There's Laurentia. I want to just get into some more details now. So I kind of gave you an idea of kind of globally what was happening around the whole world, but I want to zoom in now on Laurentia because we live basically in Laurentia. We're North America, right? So I want to zoom in on Laurentia and kind of talk more about geologic evolution of Laurentia during the Paleozoic. So Some details on the Paleozoic evolution of North America. So this is how North America was changing during the Paleozoic. So we need to talk about these things called, I'm going to introduce this idea of cratonic sequences. So cratonic sequences are just sequences of marine sedimentary rocks that are deposited on top of the craton. And basically, this comes from the incursion of ocean water. Either the oceans are rising or they're falling, they're rising and falling. And it's going to create these incursions of the ocean into the continent. And as the ocean water sits on top of the continent, it releases a lot of sediment. And those sediments build up and create these sedimentary rock sequences, marine sedimentary rock sequences we call cratonic sequences, because they're sequences of sedimentary rocks that are sitting on top of the craton. So global sea levels have fluctuated tremendously over time. You can see that how many rises and falls of sea level have there been, right? You can see there's just going, this is the red line, right? And you can just see they constantly going up and down, up and down, up and down. Okay, so sea levels don't stay constant over Earth's history. They go up and down, up and down, up and down. So here's the start of the Paleozoic at the Cambrian, going to the Permian. And you can see that during this time, we had really very high sea levels, very, very high sea levels. So this is modern day right here, right? We're about this way. And like I said, I told you before, we are at really a historic low of sea levels. Okay, there's not too many times in Earth's history in which, like we're about right here, historic lows of sea levels. So it's not in a way, too surprising that sea levels are rising. I'm not saying that it's not due to human activity necessarily, but I'm just saying that historically we're at a very low point in sea levels. So sea levels have historically been much higher during Earth history. So sea level change has been up to, if you can believe this, there's been times in which relative to the continents, sea levels have been 400 meters higher. 400 meters higher, that's like 1,200 feet higher, right? Tremendous differences. Now that doesn't have, that's in part of that is the water level actually changing. Part of that is just the thickness of the crust changing, because the crust is continuously building up and getting thicker over time. So anyway, let's talk about these different major sequences of sea level rise. I'm going to kind of explain. This is kind of a little animation explanation of what cratonic sequences are and how they form. So cratonic sequences are just craton-wide sequences of marine sedimentary rocks that were formed together during a transgression. Remember, a transgression is a rise in sea level. So here's the North American craton. Okay, let's say that sea levels rise. Okay, and as the sea levels rise, layers of sedimentary rocks form. Okay, so you can see that the North American craton gets covered with sedimentary rocks, and now you have a platform. Right, because platform is just craton underlined by sedimentary rocks. Now let's say that after that, sea levels drop. Okay, so sea levels drop, and now when sea levels drop, those rocks get exposed to erosion. So everything's going to erode. Okay, things are going to start to erode. So now we have this eroded surface. So what do you call it when you get deposition on top of an eroded surface? You're going to get, that's going to be an unconformity, right? It's going to be either a disconformity or a nonconformity, or it there could be angular unconformities. It doesn't, it just depends. But there's going to be an unconformity surface right there. Okay, so 100 million years go by, and sea levels, whoops. So you get platform, you get shield there. Okay, you get an unconformity. Now let's say that sea levels rise again. Okay, so sea levels rise again. And you get new rocks deposited on top of those old ones. So as sea levels rise again, more sedimentary rocks are deposited in a different cratonic sequence than the ones below. So that red line would be a unconformity of some kind. Maybe it's a disconformity. But you get new rocks, new sedimentary rocks put on top of the old ones. Okay, so those would represent different cratonic sequences. So there have been 4 cratonic sequences during the Paleozoic in North America that we recognize. There's the Sauk, the Tippecanoe, the Kaskaskia, and the Absaroka. Okay, these are different. The things that you see here, this is a very useful graph, by the way. The things that you see are the like bluish colored, grayish colored triangles are different orogenies. So remember that we have the Taconic. Actually, I didn't call it the Taconic. We talked about the Caledonian. I'm actually not sure what the difference, what the Taconic orogeny is compared to the Caledonian. If they're the same or different, I'm not sure. But we see the Acadian, the Ouachita, Alleghenian orogenies, right? That create that whole, right? All these orogenies put together give us the Appalachian Mountains. Okay, so that's what was happening on the Appalachian side, the Appalachian orogenies. On the Cordilleran side, so it's now the west coast of our country, we had the Antler orogeny, which was a collision of some volcanic arc islands with the west coast of our country. Okay, and the Antler orogeny, we're going to talk a little bit about that a little bit later. Okay, so now the brown color that you see, it gives you a sense of how far the sea levels incurred. Okay, so sea levels. This is showing the percent. Well, let me get rid of the ink here. This is showing you the percentage of North America that was underwater. So during this period, we had almost the entire North America underwater. Okay, so each of these brown parts are unconformities. Okay, times of unconformity. Okay, so there's times of erosion. And the white parts you see are times of incursion, transgressions of the seas, and new sequences laid down. Okay, so here are the Precambrian origins. There's the Appalachians, Ouachita. There's the Cordilleran, and we had the Sauk sequence deposited during this time. Okay, so let's talk about the Sauk sequence. The Sauk sequence gave us all of the Grand Canyon rocks. So if you go to the Grand Canyon in your life sometimes, you're going to be looking at the Sauk, which was deposited right there at the end of the Cambrian, the beginning of the Ordovician. So all those rocks in the Grand Canyon are around that age. At this time, the Cordilleran, the west side of our country, was passive margin. On the Appalachian side, on the eastern side, which of course it was the southern margin at the time, but right now it's the eastern side. Remember, you saw the rifting of the Iapetus Ocean and the conversion to an active margin. So that's what was going on during the Sauk sequences. You know, that was early, the Cambrian, Ordovician period. So the Sauk, you get, you're getting all these marine rocks, shallow marine sedimentary rocks. So you get marine siltstones, carbonates from coral reefs, sandy beach deposits, and gray would have been exposed land here. So you can see mixture of sand, silt, and limestone, basically. Remember, that should sound very familiar when we talked about transgressions and regressions, right? Shallow areas, you get sandstone. Kind of middle shallow areas, you get silt stones and shales, clay stones, mud. Here you get deeper waters, you get coral reefs that form limestones, right? So you're going to see these sequences of sandstone overlain by silt stones, overlain by limestones. That's a transgressive sequence, right? So in the Grand Canyon, specifically in the Grand Canyon sequence, where you see a very good exposure of the Sauk sequence, we get the basement rocks, the Precambrian basement rocks, the craton rocks. Overlaying the craton rocks, there is an unconformity, right? And that type of unconformity is a non-conformity, okay? And on top of that, we start to see the first incursion, shallow seas, that gives us the Bright Angel Shale. The Tapete Sandstone. Okay, the Tapete Sandstone. So this is all sandstone here on top of the cratonic basement rocks. And then on top of that, sea levels get higher, right? You get the Bright Angel Shale on top of that. And then sea levels get higher, and that's when you get the Moave Limestone. Okay, on top of that, that's the deepest part of the oceans. Okay, so moving on, that's the Sauk sequence. Moving on, the next sequence you get is next incursion of sea level. So then sea level drops very suddenly, very suddenly during the Ordovician, and then it slowly rises again. So this is showing the sea levels rising again and covering the craton again during what's called the Tippecanoe sequence that happened end of Ordovician, beginning of the Silurian. Okay, so during this time, you get the Tippecanoe sequence, and you get almost this was an amazing transgression. This covered almost the entire continent. Okay, so look at this. This is Laurentia, and you can see that it was totally covered with ocean, almost totally. Right. The only things that were sticking up were these tectonic highlands, which were from the this Caledonian the parts of the Appalachian orogenies, basically. So that's the only parts that were sticking up, along with some parts of the Canadian Shield were sticking up. So at this time, we get widespread carbonate limestone rocks covering almost the entire country. So it's amazing that you can go to all over this country, and you can find during this time, during the Silurian, end of the Ordovician, you can find very thick carbonate rocks, limestone rocks, almost everywhere in this country. And it's amazing that, you can find fossils of all sorts of marine organisms, right? So during this time, I haven't talked too much about life in the Carboniferous yet, or life in the Paleozoic yet, sorry. But we had sponges, and we had brachiopods, which are clam-like. They're different than clams, but they're clam-like. So we had brachiopods forming reefs. Kind of think of like oysters. Like hopefully some of you have seen like oyster beds around here. So brachiopods are similar. They're forming these. Brachiopods are forming these kind of like almost like oyster beds, oyster reefs. Corals, of course, form reefs. And also another creature, probably they're very much alive and well today. They're called bryozoans. So I'll talk more about all those different creatures and the difference among them in the next lecture. But this is a picture of a modern day kind of shallow coral reef. But you can kind of close your eyes and imagine, like, this is what it would have looked like for miles, like hundreds and hundreds, thousands of miles. It would have looked like this during the late Ordovician, early Silurian. Just endless coral reef, endless shallow marine, covering almost the entire world. It's pretty amazing. The continents were so flooded that there were almost just like mountain belts poking up out of the ocean, but everything else just covered with coral reef. So it was a pretty amazing time. The Tippecanoe deposited a very famous formation called the St. Peter Sandstone. It's a Middle Ordovician. Very large area of the craton was covered with the St. Peter Sandstone. So again, we have the Sauk sequence, right? That's the Sauk sequence. There's an unconformity, which would have been a disconformity. On top of that, we get the Tippecanoe St. Peter Sandstone, right? So hopefully that all makes sense. So hopefully it makes sense to you why there's an unconformity here, right? Because this was an erosional surface at one time. So, St. Peter Sandstone is very beautiful white, nice quartz sand, covers a lot of the North American craton. You can find it in a lot of different areas. So there's the Ordovician, Silurian. Like I said, a lot of the continent was totally covered. Look at this. This is a Silurian. A lot of the continent was totally covered. The only parts during the Silurian, during the peak of the high sea levels, only the Taconic Highlands, the Appalachian Mountains, the beginning of the Appalachian Mountains were exposed above sea level. Everything else was buried. The whole continent was buried. One exception to this is the Michigan Basin. I'm going to talk a little bit about the Michigan Basin. So the Michigan Basin during this time, almost the entire area of Michigan was surrounded by barrier reef that was so well extended that it created a shallow lagoon in the middle of it. And so this is basically what happens. This is a modern day barrier reef. So the reef complex, the reef is just an area so built up by organisms. Coral reef, corals, sponges, brachiopods, modern day oysters. There's all sorts of crustaceans, barnacles. Now those things are kind of modern day reef builders, but at this time it was mostly sponges and brachiopods, corals, that were building up these reefs. Okay, so they built up these reefs, and what happens is that the reef complex gets so large it cuts off the interior lagoon from the main ocean. And so basically water can kind of seep into this, but it can't get out, and it gets trapped. So the ocean water gets trapped in this lagoon, cut off from the main ocean by the barrier reef. So this lagoon gets super salty, very, very salty, because it's constantly evaporating, right? You know, you have the sun up here. I'm going to try to draw the sun. Okay, there's the sun shining its rays, and it's constantly evaporating this lagoon that's been cut off from the rest of the ocean by the barrier reef. Okay, so you get this shallow lagoon that starts to just dump out salt. And so to this day, some of the greatest, this is amazing. This is all salt. Everything you see here is just salt. This is all salt that was deposited by that Michigan Basin lagoon in the Silurian. Okay, so you could see what it's like. Just amazing salt deposits. So that's the Michigan Basin. Again, basins, we're going to talk about 3 basins. Michigan Basin is one. We're going to talk about the Williston Basin and the Permian Basin. It's all similar situation. You have a coral reef that was so developed it cut off this section of the ocean from mixing with the rest of the ocean. You get these very thick salt and evaporate deposits. Okay, so that's what happens. You get coral growth, reef growth. The lagoon gets trapped in the center, and you get these very thick evaporite deposits form. So after the Tippecanoe sequence, moving into the Devonian and the Mississippian, the Carboniferous, right? These Mississippian along with the Pennsylvanian are called the Carboniferous. So you get the antler orogeny, and you also get the Kaskaskia sequence, cratonic sequence. This is again on the west coast of the east coast of our country. Remember, we're continuing all the Appalachian orogenies, the Taconic, Acadian, Caledonian, Ouachita, Alleghanian, that give us the Appalachian Mountains. Okay, so that's ongoing. But meanwhile, we get yet another influx of the seas, kind of hitting a climax during the Mississippian. Okay, so again, during the Mississippian, from middle Devonian to late Mississippian, you get this Kaskaskia sequence. Again, a lot of the country is totally flooded with water. But now the Acadian Highlands, this is Caledonian Highlands, Acadian Highlands, right? These are all the mountains associated with the Appalachian orogeny. You get the Antler Highlands over here from the Antler orogeny. I'm going to talk about that in a minute. And now we start to get, again, another cratonic sequence of sedimentary rocks being deposited on the surface of the North American craton. And we also get the Williston Basin. So again, you get these coral reef complexes that totally surround a part of a lagoon and cuts it off from the rest. So these are areas where you get a lot of now kind of like when you had a lot of carbonate being deposited during the Tippecanoe. The Kaskaskia was more characterized not so much by carbonates and limestones, but by shale, black shale, because there's this continual development of the Appalachian Mountains, and it's pouring out all of this sediment into this shallow sea. All that sediment influx, tremendous. I mean, these are like the Himalayan mountains. They're tremendously high, tremendously well developed. You're getting collision with Gondwana, these two massive continents coming together, creating massive mountains, and those mountains are getting eroded and dumping all of this silica-rich sediment into the oceans. Okay, so that gives us these major shale formations during the late Mississippian, early Devonian, all over the country. Okay, so this is shale of Mississippian age. It's all over the place. I think this particular one is from Tennessee, but anyway, you get these shallow seas also. So some places you're getting a lot of shale. you get a lot of these kind of darker colored areas are places where you're getting mostly shale being deposited. These lighter colored areas are where you're getting carbonate bottoms. So the carbonate is developing. You can see now moving into the late Mississippian, huge development of the Appalachian Mountains. This area starts to fill in with sediment and sand. So you get sandstones, muddy bottoms and sand-covered bottoms. You get a lot of sandstones, shales being created here. It's kind of more towards the center here. You're getting carbonate, and you're getting limestone and shallow limestone seas. So here are some fossil crinoids. These creatures are called crinoids. They're sea lilies. We'll talk more about those sea lilies in the next lecture. A lot of these are preserved during the Kaskaskia sequence, especially where we get carbonate limestone deposition in the middle of our country. Again, the Williston Basin was created during this Kaskaskia, during the Mississippian sequence, and we get these barrier reef deposits. This kind of rock you see here, this is fossil limestone, a barrier reef limestone, and these kind of structures that you see here are actually fossils of stromatoporoid type sponges. Okay, so stromatoporids are a species of sponge, which was very common during the Paleozoic and is responsible for creating a lot of these barrier reef complexes. So here's a close-up of stromatoporids. So many barrier reef limestones are built out of these. Okay, so there's your black shales. We get a lot of sandstones created during this time, and a lot of carbonate rocks. Okay, so the final sequence we have in North America is the Absaroka. Okay, that came at the end of the Pennsylvania into the Permian. And this is where we see the final set of orogenies that give us the Appalachian Mountains. During this time, a very characteristic rock of the Absaroka sequence during the late Pennsylvania and the early Permian are cyclothems. So cyclothems are many of the rocks that are laid down in Pennsylvania and North America consist of in North America consists of these cyclothems. These are kind of small transgressive, regressive sequences where you get, shale, sandstone, limestone, limestone, sandstone, shale. So you get these transgressive, regressive sequences. So these are caused by cycles of transgression and regression. So what you get are these repeating sequences of delta fluvial river deposits, so like sandstones, followed by coal, followed by shallow marine, and then deep marine. Okay, so I'm going to kind of go over how this is created, but basically you'll get sandstones, and then you'll get which kind of represent like a beach. Okay, and then on top of that you'll get a sandy shale or siltstone that kind of represents like a tidal flat or estuary. This is when sea levels rise. Okay, after that you get a limestone when sea levels get higher. And then on top of that, you'll get, swamp deposits going down to shales, limestone. So you start to see these going back and forth between limestone shales. So what you're seeing are these different kind of marine and coastal deposits that are going back and forth, and it reflects a rapidly changing sea level. Sea levels going up and down, up and down, up and down. So part of the reason that we think that sea levels were going up and down during the Pennsylvanian, during the Absaroka sequence, is that Gondwana started to actually get on top. We actually had a large landmass on top of the South Pole. So when you have a large landmass like we do, right now we have Antarctica on the South Pole, it makes it very conducive to forming glaciers and getting interglacial glacial periods, just like we have right now. Right now we are at a time in which we are getting these fluctuations, relatively rapid fluctuations between glacial and interglacial periods. Same thing was going on during the Paleozoic, during the Pennsylvanian and Permian. So you had Gondwana instead of Antarctica on top of the South Pole, you had Gondwana. You have these ice sheets. When the ice sheets build up, the sea levels are low, but when that ice starts to melt, it will, I thought I had an animation here, but as this ice starts to melt, it's going to cause the sea levels to rise and flood these Laurasian parts of Laurasia, and it creates these cyclothems. So basically, kind of a breakdown of how cyclothems are created. You start off with maybe a river flowing into the ocean from the continent. That river lays down kind of a sandy, like a sandstone, right? Sea levels rise from the melting of that ice sheet on Gondwana. You get coastal swamps start to develop with some minor flooding of the, you get these lowlands with some inundated with water. It creates these coastal swamps. Sea level, that lays down coal. And then as sea levels continue to rise, the swamps die off. You get these shales created by the muddy, silty bottom of the shallow sea. And as sea levels get even higher, you start to get coral reefs form, and you get limestone deposited. So that's how you get these sandstone, coal, shale, limestone sequences. And then what's going to happen is, as it drops down, the sea levels drop down again, perhaps with glacial ice building up again on Gondwana. You get this is exposed to the surface, and the whole process could repeat again. Okay. So that's the Absaroka sequence. It consists of a lot of these cyclothems, a lot of coal-bearing cyclothems that created lots of coal. Like I said, lots of coal was created during the Absaroka. That's why we call it the Carboniferous, right? Because this was happening in the Pennsylvanian sequence. And all the coal originates from these coastal swamps that were sometimes inundated and flooded. Okay, so there you go. This is what it would have looked like during the Pennsylvanian. You can see that not as much of the land is flooded with water because the Appalachians have eroded, and they've kind of filled in and thickened out the crust over here from all of these, from all of the erosion, all the sand and sediment that's getting filled in here. You can see along here you get coastal swamps, like I just explained. You get the Ouachita Mountains starting to be built up over here, the Ouachita orogeny. We're going to talk about the ancestral Rockies in just a minute. I'm going to talk about those. They're associated with the Antler Highlands. So the Antler orogeny over here created the Antler Highlands, and it also in turn, the Antler Highlands also created in turn, or the Antler orogeny created in turn the ancestral Rocky Mountains. So I'm going to talk about those in just a minute. So you can see that much more in North America is exposed now in the Pennsylvanian and Permian. This is largely due to crustal thickening from the Appalachian orogenies and the deposition of sediment, along with the Antler orogeny and the Antler uplift of the ancestral Rocky Mountains. And also another thing that's going on that's thickening the crust is arc volcanism along the coast. Because remember, we had a subduction zone here. Okay. So we're getting close to the end. I know this is an extremely long lecture, but we're getting close to the end. So the ancestral Rocky Mountains consists of some sandstones that were uplifted very high that occurred during the Antler orogeny. So as the Antler orogeny happened, as the volcanic arc was colliding with the west coast of our country, the Antler Highlands were lifted up, as well as the uplift of the ancestral Rocky Mountains. The ancestral Rocky Mountains are basically where the Rocky Mountains are in this day, around Colorado area. So it created these very famous Garden of the Gods in Colorado. These very beautiful sandstones that were lifted up are the remnants of the ancestral Rocky Mountains. But it's kind of hard because the Rocky Mountains are kind of overlaying the ancestral Rockies, which were created by the Antler orogeny on the west coast of the country. Okay, so also we had yet another barrier reef form that created the Permian Basin, which is to this day in northern Texas and also in New Mexico. Again, it's that lagoon type environment that created a lot of evaporites, a lot of rock salt and gypsum deposits. Okay, so anyway, I know that's like a ton of information. We talked about a ton of different things, so apologize for that, but I think the last lecture was like only 35 minutes long, so it made up for that. But anyway, hope you enjoyed it. I hope it made some sense to you. We're now going to move on after this to Paleozoic life. We'll talk about that in the next lecture. Okay, till then, have a good day.